You know, I haven't been practicing the harmonica enough to play something new, so we'll have to get that on the next video. So let's just jump right into atmospheric chemistry, our first lecture on this one, and I'll have another one coming up, which will deal more with the greenhouse gases. But for right now, the main feature here is we're going to talk about oxygen. So why is oxygen so important? If I look at the two main parts of our atmosphere is 79% nitrogen and about 20% oxygen. So most of the atmosphere is those two elements. But we'll see oxygen super important for, of course, one of the reasons is when we breathe in air, we don't even use the nitrogen, we just exhale it back out because our body can't use it, as we'll see. We use the oxygen. Oxygen is the more reactive part of air, not the nitrogen. The other thing that oxygen does, besides allow us to breathe in and use that oxygen in our various biological processes, but oxygen really is the main part of the shield for us, the shielding of the high energy light coming from the sun that protects life on Earth. So let's jump right in. If I look at the two main parts, so again, nitrogen, so why is nitrogen not very reactive? Why is that? Because that strong triple bond that's holding the two nitrogen atoms together, that bond is really, really strong. I have bond energies on the Google document, 941 kilojoules per mole. What does that number mean? That means it takes 941 kilojoules of energy to break 1 mole of nitrogen apart. That's a lot of energy. That's a very, very strong triple bond. Why will our body not use nitrogen? That bond is too strong. It takes too much energy to break it down. Now, the other part, so in the troposphere, almost all of the oxygen that we have in the rooms that we're at, in our atmosphere that we experience, it's nearly all, 99+% O2. And so that is also a fairly strong bond. And it is 495 kilojoules per mole. So in order to break apart this oxygen, it still takes 495 kilojoules per mole. Still high, but enough that, but low enough that breaking of bonds can happen in our atmosphere and in our body. Now, we're going to use that to explain this variation with temperature in the atmosphere. And this is, I've just kind of crudely redrawn figure 1 on the Google document. But in the troposphere, that is our part of the atmosphere where we exist and where all the weather is. As you go up in altitude, the temperature actually decreases. So way up in the mountains, and again, this is average temperature. Obviously, it depends on weather and things like that. But on average, higher altitudes have a lower temperature. Yet that trend reverses. When we get up into the stratosphere, the temperature actually increases with altitude. How can that be? Why would it decrease and then all of a sudden start to increase? It has to do with the reactions that are occurring in the stratosphere. Many exothermic reactions are occurring in the stratosphere. And then of course we see these variations continue. That's how we define these 4 regions of the atmosphere, is how temperature varies within that region. So if we look at our O2 molecule, so this is what we've got here in the troposphere. What about when we get way up? So if I would like to refer to figure 2, which shows, well, that's kind of a crude drawing of figure 2. What I'd like to focus today is on this high energy part of the solar. So this is the solar radiation coming in. Most of it's right here in the visible section. That's why we've evolved to see only these frequencies, because that's where most of the light is coming in. And then of course we got infrared, which we'll get into the next time. That has to do a lot with the greenhouse gases. UV light is the highest energy light, and it starts around 400 nanometers. Remember from our discussion on waves, and you can review some of this, if I have a low frequency that's a long wavelength of light, that's lower energy. If I have a higher frequency, that's a shorter wavelength. So the shorter the wavelength of light, the higher the energy. So when we talk about UV light starts at 400 nanometers, that's 400 times 10 to the minus 9th meters. So right there, that is the longest wavelength that I can have and still have it in the UV spectrum. As soon as I get a wavelength that's longer than 400 nanometers, I'm into visible, I'm into violet light. Now UV also will get much smaller, so we can see, and on the figure it shows 250 nanometers, so 250 is a shorter wavelength. That would be higher energy than the 400. And so we're going to look at some of these. So we said before that 495 kilojoules per mole is what it takes to break the oxygen bond. That is about, let's see, I put that also, 242 nanometers. So I need UV light that's 242 nanometers or shorter in order to break that molecule. Now there's some other things that are occurring way up. So the light coming in from the sun, there's quite a bit. If you look at the yellow portion, that's the light coming from the sun, and the red portion on figure 2 is the light that, after all the filtering that takes place, what do we got down here at the troposphere? So of course this is the breaking of oxygen is filtering some of that, but there's also, what about the really high energy that's got the super high energy that's coming in from the sun? Let's just look at this. Oxygen being ionized by UV radiation. Now down here in the troposphere, oxygen would never form positive ions because oxygen tends to form negative ions. It's a non-metal. But up there at the very high atmospheres, oxygen, because the energy is so high, it's high enough to actually take an electron from oxygen. All this super high energy that could actually ionize oxygen, which is very high UV light, that's all filtered out at the very top of the atmosphere. That's not even getting down in here into the stratosphere. It's been filtered out. But let's look at this one, the breaking of this bond. Remember from energy that it takes energy to break a bond. This is a very strong attraction. Oxygen has its octet of electrons, and it's very happy as oxygen. To break that and rip it apart, this is unstable, oxygen by itself. To rip that apart, that takes energy in. So UV light comes in. I'll just show a little UV wavelength coming in here. UV light comes in, boom, breaks that apart. That provides the energy I need to break that apart. What happens when we put energy in? That UV light is not light energy anymore. That energy is now gone. What has become? Energy must be conserved. When I break and separate things apart, this arrangement of oxygen has a high potential energy. The more unstable something is, the higher the potential energy. So that UV light energy has become potential energy. And later, as we'll see, of course, what happens when I reform that, and they will reform, and it's not going to emit UV light anymore. When they reform, what is that going to happen? When I form bonds, forming bonds is exothermic. So when I form those bonds, I will get an increase in temperature. Okay, so oxygen is absorbing a lot of this UV radiation, but not all of it. Some of the UV radiation that comes in is actually not strong enough to break O2. But if I look at, so let's look, for example, UV light that's 300 nanometers. UV light that's 300 nanometers is enough to break a lot of bonds, right? So a lot of bonds are not as strong as O2. And if we get exposed to too much UV light at 300 nanometers, we're not going to make it. So even this light needs to get filtered out. O2, breaking this bond won't do it because that needs too much energy. This is not enough to break O2, but it's enough to do damage to life on Earth. What goes on there? That's what's happening in the stratosphere. That's where ozone exists. And so that ozone is a key part to absorbing the rest of it. The really high energy gets filtered out of the top. Ozone is in the stratosphere is what's filtering that out. Now ozone is this very special molecule. So ozone is filtering the rest. It's got a double bond and a single bond, and there's some, let's fill in these. And it's beyond what we need to go to now. This double bond is actually being shared. So it's not as strong as a pure double bond. It's a kind of a shared double bond between two. It's weaker, and so it can be broken up with 365 kilojoules per mole. So ozone, a little bit easier to break up, so all the high energy stuff, but there's still some of this other UV light that wasn't high enough energy to break this still coming through. What is going to happen? That UV light is going to come in and it's going to rip apart the ozone. The ozone is now O2 plus O, higher potential energy, and so that's where, so ozone within the stratosphere is filtering out that next part of UV light that we need to have filtered out for life on Earth to exist. Why is ozone in the stratosphere? So 90% of ozone within the atmosphere overall is within the stratosphere, 90%. Why is that? Because up here at the highest levels, most of the oxygen exists as just O, oxygen by itself, because O2 can't exist because it keeps getting blown apart. Once a lot of that really high energy gets filtered, energy UV gets filtered out, I now have a mixture of oxygen. There is plenty of oxygen now, and some oxygen by itself, oxygen O2, oxygen atoms. As long as I have a mixture of these, there's enough of them that they combine, can form ozone, and I can get this ozone. Where is that happy mixture of O2 and O? It's within this part of the atmosphere, because I've got enough light filtered out that I've got still a lot of O2 in the stratosphere. Remember that the density of air in the stratosphere is very low, but there's O2 and there's O3. So I can get that ozone formed. What's happening with this? Ozone, because it's lower bond energy, is absorbing the rest of that UV light, the stuff around the 300 nanometers and such, that we need to have filtered out to be protected from UV. So ozone does that job in here in the stratosphere. This reaction, of course, it gets broken up. Then what happens? It will, of course, find some more O2 and O, reform that, making that bond, will release energy that's exothermic. Therefore, as we go up in altitude in the stratosphere, where all this ozone is, the temperature actually increases. So up here, of course, the air is super, super, super thin, but up here the air is, the temperature is close to what it is down at sea level. There's some interesting, a little just side video, and I put a link on there, a YouTube link, for the guy that set the record for the highest skydive, and you can see he jumped from basically around the middle of the stratosphere. So he's way up there, part way through the stratosphere, and he jumped down in the highest skydive. Okay, so if you look at, back to figure 2, and I put a third figure just kind of showing a little bit of what's going on in the stratosphere. But figure 2, you'll see that it's not just UV light and visible light that's getting filtered out in the atmosphere, but also some of the other frequencies, some of the lower frequencies are being filtered. What's doing that? Other gases that we'll look at next time, CO2, water vapor, methane gas, and such. That will be part 2 of our unit on atmospheric chemistry. So until then, we'll have a good week.